page 1. Let's go full screen. That thing is recording. I see the bars moving. What could go wrong? Not much. Okay, so here is a picture of our situation. Also, we'll take our break. We'll take a 10-minute break, usually at 10:30-ish. Class starts at 9:30, usually 10:30. We'll take a 10-minute break. So usually that's our timing. So the idea here is that the position of an object at time t is given by s of t. So functional notation, t is the time value, s is representing position. So the position at time t for being on a number line is kind of boring. You're just at a number. The position at time t is 5 or 10 or -3 or pi or some number on the number line. And we are going to think of a as the initial time value. Often it's 0. And then b is going to be the terminal time value. So if a is the initial time value, then s of a is representing the position on the number line at time a. b is the terminal time. S of b is the position at that terminal time value. So maybe t goes from 1 to 5, or 2 to 5, or 0 to 10, or whatever it is. Usually we're going to start at 0. But remember that t equals 0 does not mean s is 0 necessarily. All right? At t equals 0, you could be on a cliff, not at elevation 0. Right? So t and s are representing different numbers. Now, if the terminal position, s of b, is to the right of the initial position, then the displacement is going to be positive. So if we have that standard number line and positive numbers are to the right, if position A puts us here and position B puts us here, so we start here and move this direction, we have positive displacement. And if we end up to the left of where we started, we have negative displacement. So displacement is different than distance. Displacement can be negative. Distance traveled is never negative. So we have to distinguish between those two things. When you drive to Front Range Community College from your home, you have distance and displacement. When you drive back home, you have 0 displacement, but you haven't driven 0 miles. So distance is always non-negative. Displacement can be positive or negative. It would be really cool if we had a math symbol that would represent this important quantity of displacement. Calc 1. So we have a math symbol called the definite integral. And the definite integral from a to b will in fact give us displacement. So we have this function s that's representing position. And we know of a function called the velocity, which is also s prime. If you have your position at time t and you take its first derivative, that gives you the velocity at time t. So position's derivative is velocity. And so if we integrate the velocity function, that's the same thing as integrating s prime, because s prime is velocity. Well, if you integrate a derivative, you learned in Calc 1 that the integral of a derivative gives you the function that you're dealing with. So if you integrate s prime, you get s. If you integrate f prime, you get f. Right? If you integrate a function's derivative, you get that function. The derivative and the integral are inverse operators. They undo each other. And so this gives us the antiderivative of s prime is s, and then we evaluate at b, and we subtract off s evaluated at a. Oh, that's displacement, s of b minus s of a. So we now have a mathematical symbol to provide us with displacement. We just integrate the velocity. If you integrate the velocity on your time interval, you will get displacement. So that is our first math. Any questions on those basic concepts? When you email me, you can email me through D2L or through my front range email. D2L is a pain because you can't, so if I'm on my phone and I get a notification that I have an email in my inbox coming from D2L, I can't reply to it unless I go climb into D2L. It's a real hassle. So if you email me outside of class, it's easier if you email me at my front range email address, because then I can just hit reply no matter where I am. I can be driving in my car and, well, I wouldn't do that. But I can reply to you anywhere, right? So this is a better way to email me if you have questions. That way I can just reply to it on my phone. I don't have to be in D2L, which you can be. If you have a cell phone, there is a very nice app. It's still a lot of steps. But if you have the Brightspace Pulse app, that's how you interact with D2L on a phone. Brightspace Pulse. How many of you have that app? Less than half of you. It's a really decent app if you're finding yourself going in and out of D2L and you want to be able to do that on a phone. This is a pretty decent app. So Brightspace is the company that owns D2L, and Pulse is the app. So it's a good way if you have to do email inside D2L, or if you have to jump in and see something. You can also get OneNote on your phone too, and OneNote's a little easier to manipulate than Pulse, but Pulse will work fine. Okay, so yeah. Email me there with questions. It's just easier. So let's recall some information about a definite integral. So let's suppose we imagine this happening here. This is a picture of a velocity function. So not a position function, it's velocity. So velocity is positive here. Velocity right there is 0. Velocity there is negative. So let's try to visualize what that means on our number line. When the velocity is positive, we're moving to the right. The rate of change is positive. When the velocity is negative, we're moving to the left. The velocity is negative. The rate of change is negative. So what this is demonstrating is that, okay, well, if the velocity is positive, but the velocity is approaching 0, right? Got to stop touching. So right, the velocity is approaching 0 right there. So the idea is that this object in your mind, you should be seeing it moving to the right, but slowing down, and then bang, velocity 0, stop, and then it's changing directions and going in the negative direction, because here the velocity is negative, so we're moving to the left instead of to the right. So that's what you should be visualizing. Now, when you look at the integral of the velocity function, what you learned in Calc 1 is that if you integrate a function that passes through the x-axis, you are going to actually end up with the upper area minus the lower area. If you just integrate from a to b, the integral naturally is going to do this minus that. Upper minus lower. Does that make sense to everyone? So if your function is only above the x-axis and you integrate, or the t-axis, the horizontal axis, you're going to get whatever that area is. But if that function passes through the x-axis, you get that upper area minus the lower area. Right? So that is going to be displacement. You integrate velocity. Geometrically, if you drew your velocity function, this is what's happening. This displacement is not going to equal the distance traveled, okay, because we went in the positive direction and then turned around and went to the negative direction, so that displacement's not that total distance traveled. This one will represent the distance traveled. If we take that lower area and flip it up so that all the area is positive, I'm saying that very loosely, right? Area, of course, can't be negative. When we talk about this scenario, technically we're talking about signed area. So this is a signed area, so it's a -1 multiplied by the actual pink area there, or whatever that color is. All right, so negative area can't technically be negative, but sometimes we just talk kind of loosely. The positive area, the negative area. So here, both areas are positive. So here, if this was you can think of this scenario in two ways. You can think of this as an object that's slowing down and then stopping, moving to the right, and then continues to the right, picking up speed again. Or you can think of it as the absolute value of this function over here. Okay? Over here, this area is going to represent the distance traveled, and if this was our scenario where we're going to the right, stopping, and then continuing to the right, this would also be distance traveled and displacement. It would be both. So displacement and distance traveled will be different if there's some movement in the opposite direction. All right, so let's try this geometry business. Oh, let me point out, integral of an absolute value. What kind of function is an absolute value function? Begins with the letter P. It is always non-negative. It's a piecewise function, right? An absolute value function is not integrable in one fell swoop. If you are trying to integrate this, there is no antiderivative for absolute value of something, right? The absolute value is a piecewise defined function, and if you want to integrate a piecewise defined function, you would have to integrate it piece by piece. You have to look at, so the way a piecewise defined function looks, it's like that for different pieces of the domain. So this is going to be when the velocity is greater than or equal to, I guess I don't need that. It's just greater than or equal to 0. And if the velocity is negative, then that is what you would integrate. Absolute value of v is equal to -v when v is negative. Okay, does that make sense? So if you integrate, anytime you come across a piecewise defined function, if you want to integrate it, you've got to integrate it on each individual piece. So you would have to integrate, from whatever your negative value is up to 0, and then from 0 up to your positive value, whatever it happens to be. Okay, so this would have to be done piecewise, just as a reminder. And we'll come across some piecewise function later in the semester. We'll talk about it. So let's just make sure we understand the geometry of Calc 1 here. So displacement and distance from velocity. So this is a velocity function. Consider the velocity function shown below. Objects moving on a line. Assume times measured in seconds, distance in meters. All right. So the first question says, on what intervals is the object moving in the negative direction? So somebody give me an interval where the thing is moving in a negative direction.
0 and 2.
So 0 to 2, brackets, parentheses.
Brackets.
So if you put a bracket, that means you're including. So if you included 0 at 0, is it moving?
No.
Right, because the velocity is 0 at 0, and the velocity is 0 at 2. So at those two instances, the thing's not even moving. So it can't be moving to the left if it's not even moving. So we'll use parentheses. So that interval, and then second interval,
4 to 6.
4 to 6. And same logic, right? At 4 and 6, object's not even moving, no velocity, so we don't want to include those endpoints. So part B, what is the displacement of the object over the time interval 2 to 6? So 2 to 6 in here, so we're coming all the way across. What is our displacement?
4.
So when we look at that, so displacement is going to be upper area minus lower area. So we're going to do 14 minus 10. We're going to have 4. And they gave us units. Anytime a problem gives you units, most of the time the answer should be in units, should have some sort of units. So that's going to be 4 meters. Part C, what is the total distance traveled? Time interval 0 to 6. So if we're going to go 0 all the way, whoop, that's not 6. Oh, it undid that for me. That actually is a surprise. So 0 to 6. What is the distance traveled? What do you think?
34.
Close?
44.
44. It's the addition. It's not the calculus. It's the addition. So we want to do, so for finding distance traveled, we're just going to add up all those areas. So we're going to end up with, you know, that. Yeah, so, yeah, you're on track though. So you're just adding all those areas, no subtraction. And then in D it says displacement again, but this says time interval is 0 to 8, so we're going all the way across 0 to 8, and it's displacement, not distance. So what do you think we're going to end up with?
Negative 10.
-10, exactly. So displacement, we're going to do -20 plus 14 minus 10 plus 6. So that's going to be -30 plus 20, so we end up with -10. Now no units would go there. That's just the location. Right? That's where we are ending up on the number line. Right. Oh wait, I just lied to you.
Oh, yeah.
I just lied to you. -10, it is in meters still. It is in meters. It is a number, but it is in meters. And here's the part where I lied to you. Are we at -10? Are we at -10 on the number line?
No.
No, not necessarily, because we don't know where we started. This doesn't tell us where S of 0 is. This tells us wherever we're starting, go left 20, go right 14, go left 10, go right 6. So -10 means left 10 units from where we started. So we're not at -10 because we don't know where we started. So they never gave us the starting position. So this says, describe the position of the object relative to its initial position after 8 seconds. And that's what we just talked about. So 10 meters left of S of 0. S of 0 would be your initial position. That wasn't given, so all we can say is that we're 10 units to the left. Don't know where we started. If we started at 0, yes, we'd be at -10. All right, any questions on any of those ideas? Is the Calc 1 coming back? The integral, the definite integral, upper area, lower area stuff? So as you're going through these Calc classes, Calc 2 and Calc 3, language is essential. So if there's a word you're not exactly sure what it means, let me know, because there's a lot of misconceptions. Learning calculus is like being in a leaky boat. There's no way all of you have Calc 1, pre-calc, trig, all that stuff figured out. There's always a few leaks. So as we're going through, if there's something you're not 100% sure about, ask so that I can give you clarification and hopefully some help. All right, let's go to this slide. So this kind of summarizes where we're at. So the position of an object moving at a line at time t is S of t. The velocity is S prime. So if you have a position function and it's continuous, you can take its derivative and get the velocity. displacement, S of B minus S of A, is just the definite integral. That's it. All you have to do is the integral if you're trying to find displacement. The hard thing is distance traveled because we don't have an antiderivative for absolute V. That's the hard thing. We have to break V apart into its pieces and then integrate each piece separately and then add them back together. Absolute value of V is called speed. So absolute value of velocity is speed. Speed is always non-negative. You can't have negative speed. You can have negative velocity, but not negative speed. Your speed is going to be non-negative. And then here is an application of something you learned in calculus called the first fundamental theorem of calculus. And I want you to focus for a moment. Let's put it in purple. I want you to look at this object and tell me whether that object is a scalar, aka a number, or a function. Is that a scalar or a function?
What do you mean by scalar?
Scalar is a number. So just a real number. So scalar is a real number in our context. Could be a complex number in other contexts, but a scalar just means a numerical value. So is that a scalar or a function? Okay, hold that thought. This, if I integrate from 0 to 2 the function x squared, this is a mathematical object. You need to know whether it's a number or a function. That's always what we're trying to decide. Is that thing a function or is it just a constant? Is it a scalar? Is it a number? This looks very functional because you see the x, right? You see a variable. Typically when we see a variable, we think, oh, it must be a function. But this is not a function. This is a scalar. It's written in a really weird really weird way, but that is just a scalar, right? When we go through the math, this is a scalar, right? That letter x is a dummy variable, and we call it a dummy because it's not really a variable, right? It looks like a variable, but it's not. It's a dummy variable. It's a placeholder that allows for this evaluation that gives us the scalar value of that definite integral. So that is a scalar. Even though it looks like it might be, you're integrating a function, but you're integrating a function on a finite interval, on an interval that has endpoints. So that is going to be a scalar. Versus, let's integrate from 0 to t x squared dx. Same question, is it a scalar or a function? Well, we've got this integral that needs some attention, and when we go through the math here, what we see is that we get the final value of t cubed. So this one up top is a scalar. This one is a function. All right. So back to this question, is that thing a scalar or a function?
Function.
It's a function. If you see a variable as one of the limits of integration, that's your hint that you're dealing with a function. So that means that you have a function, not just a scalar. So this is going to be a really important idea. This is how we predict the future. This tells us the position at any time t greater than 0. And the best thing about predicting the future, it's how you make money. That's how you make money in this world, if you can predict the future. And so whenever we're trying to predict the future, this is sort of what we're doing. We're saying, okay, well, this position in the future when t is bigger than 0, t is often representing time. We have our starting position, and then this is representing the displacement over the interval 0 to t, or the change, the displacement, or the change in this, the change in position over this time interval. So displacement, the change in position. Displacement, change in position. So we figure out where we start, We figure out the displacement or the change in position, add it to where we started, and we know where we are. So that gives us a way to figure out the position in the future. And if you have other functions that tell you other things about the future, right, that's kind of what most jobs are all about, looking into the future and trying to predict things. So this concept here is going to be super important. Initial position plus displacement is the future position. Okay, let's try to do this. So find some displacement from a given velocity function. So here we have a velocity function, and the question says, determine when the motion is positive, when the motion is negative, find the displacement, find the distance. So this velocity function, first we want to know, hey, when are we going to the right, when are we going to the left? Well, what we saw a couple slides ago is that the easiest way to determine when you're going positive, when you're going negative, is to look at the graph. So we want to be able to graph these velocity functions because then it sort of, the picture is very revealing. So let's go ahead and graph this. So this function, the first thing I notice is that there's a common factor between the two terms. So if we factor that out, we have that function, that representation, we can write it that way. We can represent velocity as a factored, in a factored form. And if we set this equal to 0, what are the two t values that cause that function to be 0?
Zero and 2.
0 and 2, right? Those are the two zeros of the function. So t equals 0 and 2. And what we know is that that's a quadratic function, so we know its graph is a parabola opening up or down.
Up.
So the leading coefficient, the dominant term here is the 3t squared. That's the leading term. Positive coefficient, so it's a parabola opening up. So this is all we need. Now we know, because we know parabolas, this t, let's see, t is going to go from 0 to 2. So at 0, right there, and at 2, that parabola is crossing the t-axis, I guess, is what we're dealing with here. We just said the parabola opens up. So doesn't the vertex have to be halfway in between the two zeros? And we could plug in 1 and figure out exactly what the vertex is. Doesn't really matter, though. We're just trying to get a general sense. When are we below the t-axis? When are we above the t-axis? So we really can get away with just doing something like this. Did I draw it accurately? I don't know. Until I've plugged in positive 1 and gotten that v value, plugged in positive 3, gotten that v value. We haven't, but we don't care. If you care, you can plug in the 1, you can plug in the 3 and get those values. We just want the relative position here, so it's not going to matter to us. So tell me now, what interval is this object moving to the left? 0 to 2? You agree? And should we have brackets or parentheses? Parentheses. Okay, so we're moving left on the interval 0 to 2, and then we're moving to the right on the interval, let me not put these there yet, moving to the right.
2 to infinity.
So the time interval we're given here is just 3, so we're going to go 0 to 3, 2 to 3. And on the left, parenthesis or bracket? Parenthesis for sure on the left. On the right, bracket. Because it is moving at 3, right? It is moving at 3. The velocity is not 0, so we can say that it's still moving to the right at that moment. Okay, now we want to find the displacement. So this was A. Well, I'm going to go up for B. Little finicky. So displacement, Displacement is the definite integral. And we don't have a great symbol for displacement, unfortunately. Usually we just spell it out. So we are going to integrate on our time interval 0 to 3, and that function 3t squared. Come on. That's going to be a dt. That look good? So displacement is always just the exact function integrated on the exact time interval. It's the simplest integral for this context. So we'll get t cubed over 3, the 3's cancel. T squared over 2, we get a cancellation. Let's see. I'm losing my mind. Board jumping. That does not look like a 0. Let's switch. There we go. Okay, everybody agree on that antiderivative? For a polynomial, you add 1 to the exponent, divide by the new exponent. And then we have to evaluate our definite integral. Plugging in 0 is not going to contribute anything. So just the 3, so we're going to get 27 minus... Is that 27 minus 27? All right, so displacement. Not a lot of displacement. It's like driving to school and back home again. 0 displacement. And then, last part, distance traveled. Let me just kind of get this a little bit more over there. So distance traveled. We have this area down below, and then we have this area up above. And so we have to add those two areas together. Is it obvious that those two areas are equal? Because of that, if the displacement is 0, that means the negative and the positive have to have equal area, right? It's the only way we could get a total of 0 is if this upper area and that lower area are actually equal in area, so that when we do upper area minus the lower area, we actually get 0. So that gives us 3 ways to find distance traveled. If you know that these areas are equal, so this, call it area 1, this area 2, these areas are equal, we could integrate from 2 to 3 and then double it. That would give us the distance traveled because the areas are equal. We could integrate from 0 to 2 and multiply by -2. That would also give us the distance traveled. We could also integrate 0 to 2, multiply by -1 to make it positive, because if you integrate 0 to 2, it's going to be negative. So 0 to 2, multiply by -1, and then add the integral from 2 to 3. So 3 distinct ways you could go. Let's go the simplest way. This function is already positive here, so we don't have to deal with multiplying by -1. So the distance traveled, we'll call it distance, is going to equal 2 times the integral from 2 to 3 of our function 3t squared minus 6t times dt. That look good? So integrating our function 3t squared minus 6t from 2 to 3, that's the area a sub 2, but a sub 2 and a sub 1 are the same, so if we multiply by 2, that's going to give us our distance traveled. So then we just have to integrate this again. We're going to get the t cubed minus 3t squared. This time it's from 2 to 3. When we plug in 3, we get 27 minus 27, which is 0. So we plug in the upper limit and get 0. And then we subtract off whatever we get from the lower limit of integration substituted in. Plugging in the 2 is going to give us 8 minus 12. 8 minus 12 is -4. So we end up with 8. And they didn't give us units, or they did? They gave us meters, so this is going to be 8 meters. So distance traveled is 8 meters, and this is 0 meters up there for displacement. Any questions? All right. It's 10:30. Let's take a 10-minute break. 10-minute break. And if you're like dying for more math, think about this on your break. That's not much of a break, I guess, but think about it anyway. Graph, exponential with a negative exponent. Think about the graph of an exponential function with a negative exponent. Sebastian?
So, just another refresh again.
Oh, let me hit pause on this recording. And then, great morning activities. All right, now that you've all thought about how to graph this. So again, we don't have to get fancy and precise. Our graphing is really just to get a general sense of where are we crossing the t-axis, if anywhere. What does the function look like, generally speaking, on the interval? Is it above or below? It's really all we care about, and where it crosses. So when you think of that function there, this is an exponential decay function because that exponent is negative. So let's first figure out where we are at t equals 0. Can somebody tell me what the y-intercept is, or the v-intercept, if we're being super precise with these letters? What is the v-intercept? 50. So e to the 0 is 1, and then 1 times 50 is 50. Everyone tracking?
Yeah.
So if we plug in t equals 0, that's in the exponent on e. E raised to the 0 power is 1, and then 1 times 50. So our intercept right here is up at 50. So that is a point on the graph. What is the horizontal asymptote? Exponential functions will have horizontal asymptotes, whether they're exponentially increasing or exponentially decreasing, they'll have an asymptote. What is the horizontal asymptote? Calc 1, you would have called it the limit at infinity. So what is the limit as t goes to infinity here? I can't hear you, what? How many? No. Try again. No, once was enough. I heard the right answer. Somebody said 0. So let's think about why. So math is all about, making mistakes, trying again. You can't ever just always get it instantly. You have to think about why things are. Take some percolation. If we wrote the function this way, we could turn that negative exponent to a positive, and that just relocates that factor into the denominator. As t goes to infinity, e to the infinity, remember that e is a number that's bigger than 1. E is 2.7 something, right? If you take a number bigger than 1 and start multiplying it by itself, it goes to infinity. Take a number less than 1, like a half, multiply it by itself a bunch, and it goes to 0. Right? A half times a half is a quarter times a half is an eighth. So a number between 0 and 1, repeated multiplication is going to take you to 0, but a number bigger than 1, like 2 point something, is going to get bigger and bigger and bigger and go to infinity. So this is going to go to infinity, which means the fraction has a constant numerator and a denominator that's going to infinity, so the fractions are going to 0. Right? If the numerator is a constant and the denominator is getting bigger and bigger and bigger and bigger, that means the fraction values are getting smaller and smaller and smaller and smaller. In your mind, think 1/10, 100th, 1,000, 1/10,000. Right? Those are going to 0 as the denominator is getting bigger. So this will go to 0 as t is going to go to infinity. So that tells us that the horizontal asymptote is right there. So our function, we only really care about 0 to 4. There's 0 to 4. It's going to cross this line somewhere. We don't know where, and then it's going to, this is going to continue on down towards the x-axis. So this is, approaching the x-axis or the t-axis. Bottom line is we don't really care about exactly what this y value or v value is right there. We don't care. The most important thing is that, this function is above the t-axis on the entire interval 0 to 4. So displacement and distance are the same because it never has any negative velocity. So that tells us that in part A, which I forget exactly what the question was. Okay. So it's moving right always. All right, because it's never negative. So the interval will be 0. We're going to include the 0 though because there is movement at 0. It's moving to the right, the velocity is positive at 0. And then at 4, can we include that also? Yeah, we can include that because velocity is not 0. So moving to the right. And then displacement and distance, B and C are going to be the same. Because the velocity is always positive, the distance and displacement have to be the same. That displacement is going to equal the distance traveled. Those are going to be equal to the definite integral from 0 to 4 of e to the negative, 50 e to the negative 2t times t. Okay, now we have to integrate. How do you integrate that? It's the technique you learned in the last week of Calc 1.
You remove the 50 out of the integral.
So we first can pop the 50 to the front. That is for sure. We can do that. All right, now the real question. Now what? What technique did you learn the last week of Calc 1? I know the last week of Calc 1 really sort of takes, it's kind of like RAM on your computer, just disappears. Anyone any ideas? What if we had this? What if we had the integral of e to the t dt? What's that antiderivative? E to the t. Right? So, but the issue is that coefficient of t. What do you do when there's an extra coefficient?
You make that.
Begins with a u. U sub. U sub. So we would let u equal that exponent, and then we would take the derivative of u with respect to t, du dt, and then we're going to rewrite this equation so that du is written in terms of dt. And then we're going to solve for dt because that's what we want to replace. So this becomes 50 multiplied by, okay, that's going to be e to the u, integral first, e to the u, and then dt gets replaced with du divided by -2, so du divided by -2, and this integral is with respect to u, so we need u limits of integration, not 0 and 4, not t limits of integration. We have to convert to u. How do we get our new limits? Right there. When t is 0, what is u? 0. When t is 4, what is u? Negative 8. So those are our new limits. Negative 2 in the denominator is a constant. It can factor to the front and give us negative 25. And then, what is the integral? So this has now been factored to the front, so that's sort of gone. What's the integral of e to the u du? Integral of e to the u? E to the u, right? It's the one function that's so mysterious. It is its own derivative. It is its own integral. So we have an e to the u. Limits of integration are 0 to negative 8. Got that? And so that the negative 2, so those two got combined into that. And now we just evaluate here. So we have negative 25 multiplied by e to the negative 8 minus e to the 0. This is negative 25. Can't do anything with e to the negative 8, but e to the 0 is 1. So we have that. Is that a positive number? Hard to tell. Okay, a little easier now. Is that a positive number? If we distribute this minus, it becomes a little more obvious that it's a positive number. If I distribute that minus on the inside here, this is just going to flip those two terms, and we can see that that's now a positive number because e to the negative 8 is how big? E to the negative 8? Not very big. E to the negative 8 is 1 over e to the 8. That was like 1 over 3 to the 8th or something. The denominator is huge. The fraction is tiny. So it's less than 1, right? So 1 minus that tiny number is positive. Multiplied by 25 is positive. So there is our answer. And we had units, I think, of meters. Yeah, meters, and this question was distance and displacement. So this, we should put meters in here somewhere. I want you to notice something. U substitution, vital. It is done so much in this class that we have a shortcut for U substitution when the substitution is a linear function. Our substitution was this negative 2t right there. Yeah. This is a linear function, right? Negative 2t is linear. The power is 1. Whenever we have a linear substitution, instead of doing the substitution, there is a shortcut because notice, the only thing we did was divide by that coefficient, negative 2. And we got to here. So we will see next week, actually on Thursday, we'll talk a little bit more about this. There's going to be this way that's going to allow us to do something that, in this class, we're going to call the reverse chain rule. Let me give you one example of the reverse chain rule. So first, let me remind you the chain rule. If you were to take the derivative with respect to x of, say, e to the 3x, what is the derivative of e to the 3x? E to the 3x times 3? I heard that, I think. Or maybe that's just what I wanted to hear.
No, I said it.
You said it.
I'll claim that because it's right.
That's right. She's claiming it. Everyone agree with that? So for an exponential, the derivative is itself multiplied by the derivative of the exponent. Derivative of the exponent's 3, so we have to multiply by that 3. So here is the reverse chain rule. So this is what I call it. It's what we'll call it in this class. Cal 2, we just use it so much that instead of going through all these steps of substitution, we want a shortcut. If we want to integrate this, because this exponent is linear, the integral of an exponential, just like the derivative of an exponential, is itself. So I write down the function,
Divide by 3.
but instead of multiplying by 3, we divide by 3. That is the RCR, the reverse chain rule. So we are going to be doing this so much in this class, the substitution with a linear exponent or a linear substitution. That's going to be the way we are going to lean into. Doing well in math on exams, you've got to become efficient. And to be able to just jump to that instead of doing that, this, then change the limits of integration, it's a lot. It's way faster. If you can get efficient with certain things, this is one that's easy to get efficient with. It's really helpful. But we'll talk about it a lot in this class. Whoops, not that one, that one. Okay, so position from velocity. So determine the position from the velocity using the antiderivative method and then using the fundamental theorem of calculus. So there's two different methods here. This one is the one that is going to be, I think it's a better way. It's more important. It's more revealing on the concept behind what we're doing. But the first way is a little easier mechanically to get comfortable doing. You can do either, but you really should try to focus and get this. I'll do them both right here, and you can see the difference. So, A, determine the position function. So position function, we know that the derivative of v is s, correct? I said that backwards. What is the statement? The derivative of what is what? Maybe I said it right, maybe I said it wrong, I can't remember now. S prime is v, right? The derivative of s is v. I think I accidentally said the derivative of v is s. The derivative of s is v. V is equal to s prime, right? So if you integrate s prime, you get s. So if you integrate v, which is the same thing as integrating s prime, the integral of a derivative, they undo each other, so the integral of s prime is s. So if we're trying to find s, we know that we have to integrate v. So you can do this, here is one method. This is the first method. You can do it as an indefinite integral, no limits of integration. So we integrate v, derivative of sine is cosine, derivative of cosine is negative sine. That all means that the integral of sine is negative cosine. But it's an indefinite integral, so you have a plus c. Okay, so this is not quite s yet. This is leading us to s. So this is s of t, but we're not quite there yet because we've got that mystery. So this method we get almost s, but then we have to figure out what c is to actually finish off and get s. So how do we do that? Well, we're going to look at this initial value right here. And this initial value is going to allow us to get c. So this tells us if you plug 0 in for t, the s value will be 1. All right, so that means we know that if we plug in 0 for t, s of 0 is going to be 1. And if we plug in 0 for t on this side, we have cosine of 0. So I'm plugging in 0 for t. S of 0 is 1. Cosine is 0. What's cosine of 0? So this is another piece of Calc 2.
1.
One of the hard things in Calc 2 is that we are going to use trig almost every single day. If you don't have your unit circle memorized really well, you've got to do that because you're going to be doomed as we go on because we're going to be doing unit circle values almost daily. So you want to get your unit circle down pat because it is, like Calc 1 you use it a little bit. Calc 1 you use trig identities a little bit. Calc 2 we use all the trig and all the college algebra. So it's much, that's what makes it much harder than Calc 1 is that we really are going to access all that trig, the identities, the unit circle, and all the college algebra stuff too. So it's all that stuff combined with the calculus that makes it hard. So get your unit circle out and get that memorized. Preferably visualized. When I see this, 0 is over here, right? 0 is the positive x-axis. So cosine of 0, think about the unit circle, cosine is the x value. And it's alphabetical, right? X, Y, cosine, sine. X and cosine are lined up. C comes before S in the alphabet. So cosine, sine is alphabetical, cosine, comma, sine, x, comma, y. So when I'm looking at that, I'm seeing, okay, 0 degrees or 0 radians is over there. Cosine is going to be the x value of that point on the unit circle. That point right there is 1, comma, 0, right, on the x-axis, 1, comma, 0. So cosine is 1 and sine is 0. So cosine of 0 is 1. So we're going to get 1 equals negative 1 plus c. This tells us that c is going to be 2. That gets plugged in up here. So therefore, we're going to have completed s, and we get negative cosine of t plus 2. So that is the position function. Now, that's the A method. Here's the way that is a better method to understand because it's used more generally. So, we already wrote it on the board earlier. We wrote that S of t is equal to S of 0, got to know where we're starting, plus the displacement from 0 to t of the integral of the velocity function. And here is the part we often have to be careful with. So over here, I can integrate with respect to t, no problem. Over here, I can't integrate with respect to t because t is a limit of integration. So we can't have t representing two things simultaneously. So if t is going to be this upper limit, as soon as we see that t in the limit of integration, we know we're dealing with a function. And in here, we just need a dummy variable. This is a variable because it persists. It's not a dummy variable, right? With a definite integral, if you have numbers, then that's a dummy variable. Or if you have number and a letter, it's still a dummy variable. So we use x here. So S of 0 is given to be 1. So we're going to start with 1 plus integral 0 to t v of x. So we're just going to write this as sine of x instead of sine of t. Just going to change it because we can't have a t in both the limit of integration and as the integration variable. We integrate. I guess we can just put a minus there because the integral of sine is negative cosine of x. And then we integrate from 0 to t. Now, we have to be a little careful here. We are plugging in these limits of integration only in this antiderivative function. That 1 is outside, right? That 1 did not come as part of an antiderivative. So we're not plugging in anything into the 1. We're only plugging into that negative cosine of t. So 1 minus cosine t. And if you plug in the t, you just get minus cosine t. Then we subtract the antiderivative evaluated at the lower limit of integration. So now we subtract negative cosine of 0. Oh, negative times negative is positive. Right, we subtract a negative. Maybe I'll write it this way just to be clear that it's two things happening. Right? So plugging in the lower limit of integration, you subtract it off, but that antiderivative is negative, and we're going to plug in cosine of 0. And so this becomes 1 minus cosine of t plus cosine of 0 we said was 1. And so here we're going to end up with the same thing, negative cosine t plus 2. Same answer. It wouldn't be math if we got different answers. It'd be political science. Looking at the same information and coming up with different answers. Okay. Let's try one more. This one, we're going to do it that way. So let's write down the formula first. So the position is the initial position plus the change in position on the interval 0 to t. We need to use a dummy variable because we can't have t in two places at once. So that's our formula for position. S of 0, that's 1. So 1 plus integral 0 to t. V, we get 3 sine of pi, but we're going to make it an x instead of a t, so we don't have any conflict. Yeah?
Maybe I lost it, but I'm still on where we got the negative cosine t plus 2, because when we have the second part minus the negative cosine of 0, where does the 1 minus the cosine 0 go?
Say again, where does the what go?
So we have 1 minus cosine of t minus, and then shouldn't it be another 1 minus cosine?
No, because this one is not part of the antiderivative. So that's exactly the point I was trying to make, is you have to be careful. So the antiderivative is just this yellow piece, right? This one is outside of it. It's 1 plus this integral. And the antiderivative for this integral is negative cosine of t. So this is getting plugged in just to that part right there. And this is getting plugged into just that part. That 1 is out in front. So that 1 is not part of the antiderivative. It's 1 plus that integral. Because then your 1s are going to end up disappearing. Does that make sense? So anything that's outside the integral is not part of the antiderivative.
Oh,
Right? It's 1 plus that integral. Does that make sense? We'll do another one here and let's see. If you want, you can put huge brackets and do a whole bunch of grouping to make it, maybe clearer. So this here, the 1 here is outside of the antiderivative. So if we wanted to do it with big grouping symbols, we could do this. We could put like a big bracket like that, and we'll end it in a minute. Okay, so let's look at this antiderivative. I'm going to shortcut this one with the reverse chain rule. Normally you would use substitution. If you don't have an x, if you have like a constant times x, you'd say, oh, let's let u equal pi x. And then you take the derivative and get pi, and then you divide by pi. So let's just use reverse chain rule. Reverse chain rule will work whenever this is linear. So if your substitution is linear, this is going to lead us to what we'll call RCR, the reverse chain rule. We will do this like 1,000 times this semester. The RCR is only when the substitution that you might want to use is linear. So if you were doing just chain rule, if you were to take the derivative of sine pi x, you would get cosine pi x times pi. Right? For a chain rule, you multiply by the derivative of the substitution. But what are we going to do when we're integrating?
Divide.
Divide by the derivative of the substitution. So let's go. Constants float. When you integrate anything that has a constant in front, just floats, just comes down. Constant in front. What is the antiderivative for sine?
Negative cosine.
Negative cosine. Negative cosine. So I'm going to put a negative out in front, and then I'm going to put cosine of the same angle. When you're integrating or differentiating, the angle never changes. Right? The angle has to stay the same if you're taking a derivative or an integral. Angle never changes. And now, chain rule, if you were differentiating, you would multiply by pi, but we are integrating, so we divide by pi. So that is reverse chain rule. And we kept it all bracketed off here so that it's really clear that that 1 is not part of the antiderivative. So then this becomes 1 plus, we'll just stay inside the brackets until we're done with the evaluation. So we have a constant here of -3 divided by pi. So that's a constant, -3 over pi. And then we are going to take the upper limit of integration, substitute it in for x, and then subtract off what we get when we plug in the lower limit of integration, and all that's inside these big old brackets. Constant, and then we just need to plug into the variable part of the antiderivative. And this becomes cosine of 0 again, and cosine of 0 we decided was 1. So then we're going to end up with 1 plus, we'll just leave the brackets to the very last moment just to make sure it's all clear. Cosine of pi t, nothing we can do there. Cosine of 0 is 1, so we get that. Now, when we're looking at a simplified answer, this isn't simplified because factoring like a piece of the answer and not the whole thing is worthless. Like if you have something like x squared plus x plus 1, you would never do this as a fact, right? That factoring just like 2 terms is meaningless. If you can factor the entire thing so that you have a product, that's meaningful because then you can find zeros. But just to factor a piece of it like that, we don't do that. So that's what this is right now. We want to simplify this so we distribute the 3 over pi. And when we distribute that, we are going to end up with that as our final answer. And we can't group these constants. We could put them next to each other if we wanted, but we can't combine them because they have different denominators. We could, force them together if we wanted, but we don't have to. Okay, any questions on that? Any piece of that hopefully some bells are ringing, and hopefully they're not warning bells. Hopefully they're motivation to study bells. All right, let's take a look at velocity. So we're going to generalize this concept. So we just found position from velocity. We can do a similar thing and find velocity from acceleration. So we have this little chart, this little direction thing. We have the direction that looks like this. So we have s that turns into velocity with a derivative and then turns into acceleration with another derivative. Or you go backwards. So what we just did was take velocity and we integrated to get to position. So if we have acceleration, we would integrate it to get to velocity, and then we could integrate it again to get to position. So if you know the acceleration at time t of some particle moving back and forth on a line, integrate twice and you can get to its position. Start with acceleration, integrate to get to velocity, integrate that to get to position. So that's what this is representing. Same fundamental theorem of calculus concept, the velocity at time t is the initial velocity plus the change in velocity. And the change in velocity is the integral of velocity's derivative, which is acceleration. So that's the same fundamental theorem idea. And so then, if you're not dealing with physics, where you've got a particle that's moving back and forth with position, velocity, and acceleration, if you're dealing with financial markets or populations, instead of using this physics application, you can generalize and say, hey, let's just let Q be some quantity and its rate of change is Q prime. You can do the same thing. And this is what most fields will use. We want to predict the future value of something, the population of whatever, population of people, population of animals, initial position, not position anymore, but initial population, so the starting population. And then this quantity is going to give you the change in population over time, and then we add those two together and we predict what's going to happen in the future. So this is a generalization of the physics. The physics concept you can really tangibly understand, and then we generalize it to more general situations. So that is going to be where we're going. So let's do one of these where we start with acceleration. And let's build velocity and position. Okay. So velocity at time t will be the velocity at time 0, starting velocity, plus the change in velocity, which is the integral from 0 to t of velocity's derivative, in other words, acceleration. So that is our formula. Initial velocity plus the change in velocity. When we were talking about change in position, we had another word called displacement. We don't have a word for change in velocity other than change in velocity. We don't have another word like displacement, but that's what it means. It's sort of like the displacement of velocity, the change in velocity. And we can just truck on. So this method with the fundamental theorem of calculus is nice because you don't have to go substituting back like we did with the other method. So 50. What's the antiderivative for negative 32?
Negative 32x.
Negative 32x. Right, if you integrate a constant, you just use whatever your variable is. So this is going to be negative 32x. And that will then have limits of integration from 0 to t. So the antiderivative, negative 32 with respect to x, so negative 32x. And now here again, we have to be careful because the antiderivative is this piece. Right? The 50 is in front. That 50 is not part of the antiderivative. So the 0 and the t have nothing to do with the 50. So first we plug in the t and we get negative 32t. And now we subtract off antiderivative at 0. So minus a minus is plus 32 times 0 is 0. So here is our velocity function. Things that make you say, math. Does that make sense? Everybody clear? The 50 is on the outside, so we plug in the t here, we plug in the 0 here, and then we take the difference. Upper limit minus lower limit. Now do it again. So now we have s of t will be s of 0 plus the change from 0 to t of velocity, which is 50 minus 32. Oh, can't use t. We already used t, so we put an x. And s of 0 is given to be 0. We'll put it there for a moment. And then we integrate this. So the integral of 50 is 50x. The integral of negative 32 will be, negative 32x will be negative 16x squared. That goes from 0 to t. This is the antiderivative in here. That number out in front, 0, in this case it doesn't matter, but that 0 is not part of the antiderivative. So the 0 can vanish now, and we end up with 50 times t minus 16 times t squared. And when we plug in the lower limit of integration, what do we end up with? Yeah, just 0, so we don't need to put anything else. That is position at time t. So from acceleration, we integrate once to get to velocity, we integrate again to get to position. All right, you ready to try one? Okay. So you do this one parallel to the one we just did. Raise your hand if you're stuck and I can give you a jab. So exact same process. I'll write the general formula here just in case you're I'll put the two generalist forms of these up here just in case. That's an S. We'll do them one at a time. We'll do the velocity first. Anyone have questions with that velocity? So here's one of those antiderivatives where we don't have just the t in the exponent. So if we have integral of e to the negative t dt, this, what is the derivative of this exponent? Minus 1. So if we had, if we think about just that, the derivative is equal to negative 1. So here's where we use that reverse chain rule. And the integral of an exponential is always itself. And then when we're integrating, then we would take that and we divide by that derivative, that constant value. And then add a constant integration equation. So in the end, we just end up with that. And you can always double check. If you took the derivative of this, the derivative of an exponential is itself, and then you would multiply by the derivative of the exponent, and that would turn that back into positive. So you can always double check by going backwards. So it's one of these things, we're going to see a lot of these. So if we have e to the 5x, we would end up with e to the 5x. These two? Yeah. So the dividing by the negative 1 is just going to, it's just going to modify the coefficient there. So think of this as a positive 1 right there, and so we can think of the coefficient as 1 divided by negative 1.
Thank you.
Yes. All right, so let's go through this first one. We're going to start with V naught, which is 60. And then we're going to add, so that's the initial velocity, and then we're adding the change in velocity. The change in velocity means the integral of its derivative. And the change in velocity, when we integrate its derivative is acceleration. And we just have to make sure that we use a different letter. So we'll use an x, or whatever letter your favorite letter is. Zeta, whatever letter you want. Beta, zeta, eta, neta. So that's what the next step would look like. We just replace v prime with what v prime is equal to. V prime is acceleration. And now we're going to integrate, and this is a reverse chain rule because this exponent is linear. If this is linear, you can always use reverse chain rule. Ugh. Really? Okay. I was gentle. I went slowly. So that is linear, so we can always use reverse chain rule. The derivative of that exponent is -1. In Calc 1, when you did derivatives with chain rule, you would multiply by that -1. Here we're doing integration, so we divide by -1. Not that it really matters. Division and multiplication by -1 do the same thing. So here the integral of an exponential function is always itself, e to the -x. First thing you always do with the derivative or an integral of an exponential is write down the function again. And then the derivative of the exponent is -1, so we're going to divide by -1. So there's the antiderivative right there. Itself divided by the derivative of the exponent. And that gets evaluated 0 to t. And once again, we're only evaluating this. That's the antiderivative. The 60 is secondary. It's not part of the antiderivative. So we will get 60. Now we'll plug in the t. So we're going to have -e to the -t. And then we have to subtract off the antiderivative at 0. When we subtract off this negative, that turns into a positive. E raised to the 0. And what's e to the 0?
1.
1. So our final answer here is going to be 61 minus e to the -t. That will be the velocity function. All right, any piece of that is causing you grief? Sebastian?
Yeah, so I have a quick question on where you got the 61, because when I plug in the 0 on the e to the power of -x, I know that it was going to be turning into 1, but wouldn't you be dividing into -1?
So when we evaluate here, it's this antiderivative evaluated at t minus this antiderivative evaluated at 0.
Oh, yeah.
So there's that built-in minus. It's the upper exponent plugged in, and then you subtract off the antiderivative at the lower exponent. So we're subtracting a negative.
Right, gotcha. Yep.
Does that make sense? Subtracting the negative is what makes it a positive. Yep.
How did you get the e to the 0?
When we plug in 0 for this x, e,
Oh, shoot.
you see it?
Yeah.
Good. It's quick. You can see it that fast, it's good. All right, and then for the position function, initial position is given to be 40. So we're going to have 40 plus the integral from 0 to t of s prime. S prime and v are the same thing. So this is the function that's going to go in here. With one modification, we can't duplicate t's. We already used the t as that limit of integration, so we just use a dummy variable. Pick your favorite letter. So let's go through this again. So now the 40 is out in front, and now we're going to integrate. So we're integrating term by term. This is the antiderivative, so 61 times x, integral of a constant, constant times the variable. And now the integral here. So the integral, we already saw the integral of e to the negative x is going to be itself divided by -1. But we have a minus there. So it's going to be minus e to the negative x itself divided by -1, 0 to t, and we can even put parentheses in here if we want to distinguish that that's the antiderivative. So before we simplify any, or before we plug in our limits, let's just be clear that this becomes, and we'll put our grouping symbol in here, right? Negative, negative, turn it into a positive. So this is our antiderivative right there. 61x, e to the negative x, but you divide by -1, which makes that positive. And then we can plug in to our antiderivative, not the 40, 40's out in front. Plug in the t and we'll get 61t plus e to the negative t. Now we subtract off what we get when we plug in 0. So we've plugged in the upper limit there, and now we subtract off what we get when we plug in 0. Maybe we can even put it in parentheses if we want. We're going to subtract off this whole thing evaluated at 0. So that's going to be 0 plus e to the 0, whatever that turns into. Everyone agree with that? So here's the antiderivative with the t put in. Here's the antiderivative with the 0 put in. We do subtracting the two. So what does this end up being? What is e to the 0? 1 plus 0. So this whole thing is -1. So that makes this 39 plus 61t plus e to the negative t. This will be position at time t. So this is the part that you were asking about, Sebastian, right there. There's that built-in minus sign. Upper minus lower evaluation of the limits. Any questions before we go to the next slide? Yeah, this stuff all takes a lot of practice. A lot of practice. Application, let's talk about an application. So instead of talking about the physics application where we're looking at position, velocity, and acceleration, let's look at a population. So we've got a population. This is what you can measure. If you're a biologist, you go out and you measure the change in that population. So somebody is going to go out into the world and measure the rate of change. That's something that we can do empirically. We can go out and measure with instruments or whatever. There's ways to measure whatever you want to see that's changing. You can get an equation that's measuring the change. They bring it back to the company, and then the math people are going to build the function that's going to predict the future. So there we have our rate of change, and we want to use that to predict things. So let's see what happens. So the population, and I'm going to do B first. B makes more sense to do first. That's the whole point. Like, let's build P of t. If we can build P of t, then we can plug in the 15 and the 35. Once we know what the P function is, we'll evaluate it. So we'll do that first. So P of t is P of 0, starting population, plus the change in population. Well, the change in population is the integral from 0 to t of the derivative, but we're going to put in an x instead of a t because we already used the t. So that is the general equation. That's the Q formula we saw a couple slides ago for general quantity. Here they use a P instead of a Q because it stands for population. So how many foxes do we start with? We start with 35. Plus, we're going to integrate on the interval 0 to t, the rate of change. which is 5 plus 10 times sine. I'm going to rewrite this coefficient, this angle, a little bit differently. It's a little easier to take a derivative when the coefficient is more looking like a coefficient. It's not kind of commingled with the denominator, right? You can think of that as pi over 5 times t. All right, so we've got our 35 plus, so integral of 5 is going to be 5. We're integrating with respect to x now, so 5x. Integral of trig function. So first, let's think about the function. The function is sine. Integral or antiderivative of sine, we've already done it a couple times today. Integral of sine is
Negative cosine.
negative cosine. So there's the negative there. The coefficient doesn't change when you take a derivative or an integral. The coefficient just floats. And we found that for sine, it's going to be negative cosine. Angles can't change. So there's the first part. Drop the coefficient, pick the right function, negative times cosine. Angle has to stay the same. Now we have to do the RCR business. This is a linear function right here. That is linear. That tells us that we can use RCR, we can use the reverse chain rule. You could use substitution. If you want to do 5 extra steps, you can do substitution. Totally fine. What is the derivative of this quantity?
Pi over 5.
Pi over 5, right? If you have a constant times x, its derivative is that constant. Derivative of 7x is 7. Derivative of pi over 5 times x, pi over 5. So the derivative is pi over 5. That is the part that we have to divide by. So down here, the reverse chain rule part, we are going to divide by pi fifths. And then this all gets evaluated on the interval 0 to t. If you want to be super careful, you can put in your grouping symbol here. Maybe we should use brackets since there's already parentheses in there. So you can put those in. You don't have to, as long as you're, as long as it's clear in your mind that the 35 is not part of the antiderivative. Whatever works. So we have 35. First step is pretty easy because we're just taking all the x's and turning them into t. So we're taking the antiderivative, plugging in t, antiderivative, plugging in 0, and then subtracting. So plugging in t, that's pretty easy. So we get 5t minus, let's do this math. When you divide by a fraction, isn't that the same as multiplying by the reciprocal?
Yeah.
So that's going to be 50 over pi. So minus 50 over pi. Cosine pi over 5 times t. There's our angle. Now we're going to subtract off the antiderivative evaluated at 0. So I'm going to just bracket this off. So there is the antiderivative evaluated at t. Now we want to subtract off. I'm going to put the minus, and then we're going to put the antiderivative evaluated at 0. So right here is the antiderivative evaluated at 0. When you plug in 0 to this first term, we of course get 0. And we'll put it in here just to be safe. 0. And then minus, and we'll do that math out in front again, 50 over pi times cosine of 0. And that's it, right? So anti at the upper, anti at the lower, and subtract the 2. This allows us to simplify then. 35 plus 5t minus 50 over pi cosine pi over 5 multiplied by t. And let's see, this becomes a plus plus how much? Plus 50 over pi. Because cosine of 0 is once again 1. So 1 times 50 over pi is 50 over pi. We could collect these constants and put them next to each other, but they're not like. We can't add them together because they have different denominators, so let's just leave them alone. And that will be our population at time t. So that's the population of foxes in the future. And the question then said, well, what's the population 15, 35 years later? Started with 35. That's the model that we got by going out into the field and measuring. This, in practice, is probably only going to be good for a specific number of years because of the way population cycles happen and prey and all that stuff. So 15 and 35. If we want to evaluate that, P of 15, don't we just plug in the 15?
Yeah.
Once we got the function, let's use it. So if we plug in the 15, we're going to get 35 plus 15 times 5 is 75 minus 50 divided by pi cosine. Plug in a 15 there, and I'm seeing 3 pi plus 50 divided by pi. Okay, cosine of 3 pi.
0.
I hear a 0. Let's see. So unit circle, we're at 3 pi. So it's 3 halves, right? So we're on the right side of the unit circle, and then 1 pi, 2 pi, 3 pi puts us on this side of the unit circle. So cosine is
-1.
-1. Yep. So this is all going to become 110. That's going to be -1. So this part right here is -1. So that's going to make this positive. So we have 50 over pi plus 50 over pi, which is 50 over pi plus 50 over pi.
Oh, so
How many pi's? 100 over pi. Common denominator, combine the tops. So 50 over pi plus 50 over pi is 100 over pi. The math is getting really hard now. Ugh. Okay, so there is P of 15. Obviously, we could get an approximation, plug it into a calculator, round it to the nearest fox. We'd have that. P of 35. Maybe we won't write this all the way up. So this is going to be 35 plus 5 times 35. I'll just write this out. If you want to simplify, you can. I think you get the idea, though. So you're just going to replace the t with the 35, combine all the constants. If you are asked for an approximation, then you are going to plug it into your calculator and round to the nearest fox. Is it time? All right, let me say one last thing. The final slide here is just the summary. This sort of just talks about the physics application and the generalization to Q or P. So on Thursday, we'll start with 6.2. Go ahead. One thing to be successful in calculus is looking ahead. When I was a student, we went to class 50 minutes a day for 5 days a week. You guys go to school 2 days a week for 2 hours and 15 minutes. If you don't look ahead and you get lost in the first 15 minutes of class, you've got 2 hours of being in a hole, which we all know being in a math hole is not fun. You've got to, so look ahead. You always want to be doing that in these upper level courses to make sure that you kind of have a sense of where we're going. No spiraling. I can't even say the word. Spiraling. Not allowed. All right, see you all Thursday. Thank you for coming. Welcome. Happy New Year. Yes. So homework is always in my math lab, and the homework is always going to be due just before the exam. So it's not due, but you should do homework based on whatever we covered. So we finished 6-1, so you should be able to finish the 6-1 homework by Thursday. And then you can ask questions on it on Thursday if you have anything or stuff. Yeah, good question. I should have mentioned that. So if you click on the link in D2L, so let me just pause the recording. Will it work?